Okay, so the two topics that we're doing this term, trigonometry and quadratics, I've said to a few of you a few times that these topics are starting to aim towards the advanced level of maths next year. And this section of maths that we're doing today is a good example of something that is definitely directed towards advanced maths. If you do standard maths, you will not have to worry about what we're going to do here. Okay? Now you know that trigonometry, well, maybe you know, trigonometry's been around for a really, really long time, right? It's actually been around since the 13th century. So way back then, they did not have calculators. So they had to have other ways of finding their trig ratios. And where it actually comes from is a circle. Trigonometry that we've known for so long with all these different triangles, but it actually has a lot to do with what we call a unit circle. Now, a unit circle means a circle with a radius of 1. That's what I mean by unit. One unit. One is the radius. Okay? And all the trig that we have done, or most of it anyway, we've always been using acute angles. Okay, so angles between 0 and 90 degrees, which are angles in what we call this first quadrant here. And I'm going to call it up here, this is my theta quadrant. We've had angles in there. So there's a line drawn in that quadrant. And to save us some time, I'm not going to get the protractors out. The angle that is in there, if I was to measure it, that's a 40-degree angle. So they would get their protractors out. They'd measure the angle that they're wanting to find sine, cos, or tan of. So we're choosing a 40-degree angle. And they've got to find out what, let's say, sine of 40 is equal to without a calculator. Can you imagine? Okay. Now we know that sine is equal to opposite over hypotenuse, correct? So if they would draw this little triangle in here, this little right angle triangle, the opposite is this side here, which I'm going to call y. The reason I'm calling it y is because the height of that line is the y value on that Cartesian plane there. Okay? And when I need it later, this side here, I'm going to call the x, because it is how long across that x-axis that side is. So if I was trying to find, let's start with sine of 40 degrees. Sine, as I said, is equal to opposite over hypotenuse. From my 40 degrees, the opposite is the y, and the hypotenuse is 1. So it's y over 1, which is just y, right? So what is the length of y? This unit circle, it's on grid paper, so it's not a great scale, but it is actually to scale. They would actually get their little circle out here and they would try to count off, read it off that graph. So this is 1, what have we got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So each one of those spaces is 0.1. So this is 0.1, 0.2, 0.3, 0.4. And there's my 1 right at the top. So approximately, okay, this y line here is, what do you reckon that is? 0.65. Type it in your calculator. What is sine of 40 in your calculator? All right, I've got one. Oh, wait, mine's in radians. Let me just change that back to degrees. So sine of 40, oh, we were pretty close for that dodgy scale, 0.64. Okay, that's how they did it, without a calculator. Now, we don't want it, we're not going to be going back to the Dark Ages here. I'm not going to be expecting you to read things off the unit circle, but it does help you to see how we're going to apply this to other types of angles. And today we're going to start with, not only, obtuse angles. Okay, obtuse angles, if here is, I'll write it on here, if this is 0, I'm starting at 0 degrees, and we measure an angle going anti-clockwise, so do not confuse this with bearings, because bearing starts at the top and goes in a clockwise direction around. These ones always start here, and we go anti-clockwise, so 90 is there, which means that 180 is going to be here. while I'm at it, 270 is down there, and 360 way back around to there again. Okay, so if I now want to look at obtuse angles, okay, obtuse angles means between 90 and 180. One of the really cool things that they discovered was if they grabbed their protractor out and they drew a line that was 140 degrees, again, I'm not getting the protractor out, but there you go, that one there, from the start, from the 0 all the way around to there, if that angle there is 140 degrees, it has the same height as that one in the first quadrant. So sine of 140 degrees is also equal to 0.65 or 0.64 if we were using our calculator. That's really cool. It means that there is actually angles that have the exact same answer. Like, there's actually 4 of them, because you can go all the way around the circle. We're going to do that later. We're going to start with 2 for now. But there's actually 4 different spots around that diagram that will give you the same, pretty much the same answer each time. How do we find them? Well, the angle in that first quadrant we call our reference angle, the acute angle. You'll hear that word a lot. You'll see it in the exercises. So that 40 degrees is my reference angle. If I want to move that into the second quadrant, which I call the obtuse angle quadrants, it is going to be 180 minus that reference angle to find the one that's the same. 180 minus 40 is the 140 that I used, wasn't it? Okay, if I chose 10 degrees as my reference angle in here, it would be the same as 170 in the obtuse angle quadrant, right? Okay, because it's always 180 minus. And so what you'll find is, however, I've only done sine. Sine is positive there. Let's quickly have a look at cos though. Cos of 40. All right, sine is opposite over hypotenuse. Cos is adjacent over hypotenuse, isn't it? So the adjacent is the x over the 1. To the x this time. What does x read on here? 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7. What do you want to guess that is? 7.3? Maybe? 2, 3, 4, 5, 6, 7. I'm going to go 0.75. Keep it in the middle, approximately. It's not a great scale. You'd have to have a much better scale on there to get that second decimal place more accurate. I think it's actually about 0.77 if you type it into your calculator. If I was to go to the obtuse angle for that one, so cos of the 140 degrees, it has, if I draw the line down here, it's going to have the same length, but what's the difference? Like, it's still the 0.75, but that's a positive 0.75. If I'm going this way, it's going to be negative 0.75. And what about tan? Tan of 40. Now, one of the cool things about tan is it's actually sine divided by cos. So, because you can't actually draw, you could do, actually no we can't, all right. Tan is opposite over adjacent. So opposite is the y and the adjacent is the x. If the y was 0.65 and the x is 0.75, that comes out to be approximately 0.65 divided by 0.75, 0.87. Thank goodness for calculators, right? Okay. What about if I did the obtuse one, tan of 140, the opposite over adjacent is the y over the x, but we're talking about the one in this second quadrant here. The y is still positive, which was 0.65, but we worked out that the x value is negative because it's on the left-hand side of my graph there. And when you divide those, you're going to get the same 0.87, but a positive divided by a negative is a negative. So what you find is there's 3 rules that we're going to get out of this. The first rule was that sine of an obtuse angle. Now, to show that it's an obtuse angle, as a formula, I'm going to call it 180 minus theta because that was that second quadrant. Theta is always my reference angle, remember. Acute angle. Sine of something in that second quadrant is the exact same thing as sine of that reference angle. Cos of something in that second quadrant is cos theta, but it's going to be negative. That's the only extra catch. And the same thing with tan. Tan of 180 minus theta is also going to be equal to tan theta, but negative. Okay, so they are our first 3 rules for the day. Going to be a few rules today, I'm sorry about that. A few things to remember. So we'll keep that in mind. Let's have a look at the next page. There's some other rules here I need to show you. And you might have seen these briefly at the end of exercise 7b. Question 15 at the end, I think, kind of saw a glimpse of these. Again, because I guess they didn't always have calculators. And also for us, especially with applications of maths in science, we don't always want to have to give decimal answers to things. Okay, if we have to round something and then do further calculations, it means that there starts to be errors involved with what we're calculating. And when you talk about massive distances in space or whatever else, those errors can be quite significant. You don't want to have to round things. So preferably, we would like to leave things exact. Okay, so there's actually more. There's 3 that we're going to learn about here. 3 angles, the 45, the 30, and the 60 degree, that we can actually work out exactly rather than having to type them into our calculator. Okay, and they come from these 2 diagrams. A brief explanation of where these diagrams come from. The first little one here comes from a square. The smallest square that you can draw would have a side length of 1, right? Properties of a square is that if you draw a diagonal, it will bisect the angles in the corner, making these 45-degree angles. Okay? And then using Pythagoras Theorem, if you did 1 and 1, so big square root of 1 squared plus 1 squared is going to become the square root of 2, which is how you get the hypotenuse. Okay, and so you can see this is my diagram here. I've just reduced it to that little triangle there. Here's my 1 and 1, square root of 2 for the hypotenuse and the 45-degree angles. So if you want to find sine of 45 exactly without using your calculator, sine is opposite over hypotenuse. In that triangle, I'm just going to use that 45 degrees, you can use either. Opposite is 1 and hypotenuse is root 2. So sine of 45 is 1 over root 2. Now let's have a look at, we've got the 30 and the 60 in there as well. The other triangle comes from, actually no, let's do cos before I move the other triangle. What about cos of 45? Cos of 45 is going to be adjacent over hypotenuse, which is also 1 over root 2. And since I'm still stuck on 45, tan of 45 is opposite over adjacent, which is 1 over 1, or in other words, 1. Okay, so I've dealt with, they're the 45-degree ones right there. The 60 and the 30 comes from this other triangle, this other diagram. Brief history where that comes from is an equilateral triangle is your starting shape. Because an equilateral triangle, what are all the angles in an equilateral triangle? 60. Okay, so you've got 60 and 60 here. I won't draw the third one in there. Because what they do is to make it a right angle triangle is we bisect the top angle to make your perpendicular height in there. And that's where you get the 30 degrees from. So there's your 60 and your 30. Okay? Now, with the square, we did the shortest side length we could use was a side length of 1. The shortest side length you could use in this triangle would be a 1, but because I've had to bisect this bottom side, I don't want to have to go to like side lengths of a half, right? So instead, we make the shortest side length a 2. So if the sides are all 2, it's 2, 2, and then when I split that, it's 1, 1 on each side, right? And that way I don't have to go into decimals if I make the sides all 2. Okay, so all we do is we just take 1/2, we take that one triangle there, and I make this right angle triangle, this triangle here, right angle, and I use Pythagoras Theorem to get that third side, that last side there. So it's finding the shorter side, so it's subtracting. Square root of 2 squared minus 1 squared, which is 4 minus 1, which is root 3. Okay? You don't have to memorize where it comes from. It's just kind of cool, don't you think? Anyway, there are those triangles that you will have to know. Okay? I suggest you memorize the triangles, not this table that's below, because it's far more complicated down here. But let's go through and work out what all the 30 degrees ones are now. So let's start with our 30 degrees. Here it is. If I want to find sine of 30, sine is opposite over hypotenuse, which is 1 over 2. So sine of 30 is equal to 1/2. Okay, let's do cos of 30. Cos is adjacent over hypotenuse. Adjacent is root 3, so root 3 over 2. And lastly, tan of 30, tan is opposite over adjacent, which is 1 over root 3. Okay, now the 60 degrees. 60 degrees, starting with sine, 60 is opposite over hypotenuse, root 3 over 2. Does it make sense how I'm getting these? Cos 60 is adjacent over hypotenuse, which is 1/2. And tan of 60, tan is opposite over adjacent, which is root 3 over 1, or just root 3 over 1. Doesn't need to be there, right? Okay, so those ones there, they are the exact values that come from those triangles. In the exercises that you do, please be prepared to rationalize your denominators. If you have to do calculations with these afterwards, remember doing surds? Okay, so you'll often see, okay, if this was my answer, for example, the textbook wants that to be rationalized. So they're going to go, all right, how do I rationalize that? So it's 1 over root 3. You times by the root 3 over root 3. Trying to get the surd off the bottom. 1 times root 3 is root 3. Root 3 times root 3 is 3. Okay, so sometimes you might look at an answer in the textbook and go, I'm sure I've done this right, but it's a different answer in the back of the book. It's probably because they've rationalized their denominator. That might be the only difference there. Okay, so just look out for that and try to remember to do that yourself.
Will we get marked down in the test if we don't rationalize?
I'll have to look into that. I'll let you know. Okay? All right. So, as I said, there are a few people out there who just like to memorize all these exact values, but I often find that people get confused if they try to do that. The best thing to do is to be familiar with these triangles and do what we just did. If I want to know sine of 30, you have this triangle here, sine is opposite over hypotenuse, and you do it from the triangle every single time. Now, the ones that I didn't do is the 0 degree and 90 degree. Okay, those are ones of what we call boundary angles, and they come mostly from the trig graphs. But because we haven't done those yet, I'm not going to spend more time showing you the trig graphs right now. We've kind of dumped a lot on you already. So for now, any multiple of 90, so remember that diagram back here where I had the 0, 90, 180, 270, 360? Those 90s, so on the crosshairs of your Cartesian plane, any angle that you've got on there, it's either going to be 0, 1, or minus 1. And let's just type them into your calculator because that will keep it really simple. So let's go through and do those for our table here. Let's type sine of 90. So sine of, 0 was the first one. Sine of 0 is 0. Easy peasy. Next one, sine of cos of 0 is 1, and tan of 0 is 0 as well. And let's do the 90 degrees. Sine of 90 is 1, cos of 90 is 0, and tan of 90, oops, is an error. It actually is right when I did that. I didn't make a mistake typing that in. It actually is what we call undefined. Tan cannot be defined at that section. So write in there, undefined. Oh, can't spell defined. Defined. There we go. All right. Okay. So that was a quick little reprieve. Here it comes again. Back to my unit circle. So I talked about my 40-degree angle, okay, and we saw that there was a pattern that we had the 180 minus theta angles in there. Now, we actually want to apply that to all 4 quadrants. Dumping a lot on here today, because now we're going to go to all 4 quadrants. If this one here is my theta quadrant, we've already learnt that this one here is my 180 minus theta quadrant. The angles that you measure, the key thing is that it's always measured from this horizontal line. Okay, that's your starting point. So the angle that's been chosen for this one, this little dot that's been put on here for you, if you draw a line coming out to that, it makes a 30-degree angle. Okay, so change the angle to 30 degrees here on us. 30 degrees right there. So in this quadrant, my 180 minus theta quadrant, how big is that angle? From here all the way around to there, how big is that angle? Remember, if the theta is 30, 150, perfect. I'm going to write it here at the end, because otherwise I'm going to get too many lines drawn on this thing. That one's a 150-degree line. That one was 30 degrees. Because now I want to go down into what I call the third quadrant, going below. And this one is what we call the 180 plus theta quadrant. This is my 180 line, remember? And I want to plus on the 30 degrees down to here, which means that that one's going to be 210 degrees. And to put it into the fourth quadrant, this is the 360 minus theta quadrant, because 360 is the whole way around to this line. And then go, we just want to subtract that angle back off to come back down here. So 360 minus 30 is 330 degrees. So a quick little investigation. Grab your calculators, because we want this to be fast. We've spent a lot of time on this. Type in cos of 30. What do you get? 0. Yep, that'll do. Cos of 150. Oh, we're going to be faster than that. Negative 0.87. What about cos of 210? Yep. And cos of 330? 0.87. So what you can see is we've found the spot the whole way around that all stations are central. 4 spots where they have the same decimals. The only difference is that 2 of them are positive and 2 of them are negative. And the key thing we need to learn here is where. We need to know where cos is always going to be positive and where is cos going to be negative. Okay? Let's do sine now. Type in sine of 30. Yes, 0.5. What about sine of 150? 0.5 again. Sine of 210? Negative 0.5. And sine of 330? Cool. All right. All the same value. 2 positive, 2 negative. All right. What about tan? 0.57. Tan of 150? Yep. Negative 0.57. Tan of 210? 0. Yep. And the last one will be negative again. Okay. So what you can see by this quick little calculator practice we did here, all the all of the sine, cos, and tan of the 30 degrees. So the ones that were in this first quadrant, every single one of them was positive, weren't they? So this quadrant here is what I call the A quadrant, which stands for all. Everything in that quadrant, sine, cos, or tan of any angle between 0 and 90 degrees will always be positive. Okay, look at the second line. Cos, negative. Sine is positive. Tan is negative. Sine is the only one that is positive in this second quadrant. So we call that the S quadrant, meaning that only sine of any angle between 90 and 180 will be positive. Cos or tan, though, would be negative. And, all right, third quadrant, these ones. Cos is negative, sine is negative, t is positive. So this is the T quadrant, where tan is the only one who's positive. The other ones are negative. And I think you see what's happening here. What's happening in the last one? Cos is the only one who's positive. So C for cos. So you will often see this diagram here referred to as, you'll hear the little acronym, all stations to central. To remind you where things are positive and negative. You know when you catch a train? All, and then all stations to, do they still do that? 3 nations have been on a train. Okay. A, everything's positive here. All, S for stations, cos, tan to central. All stations to central to remind you where they are positive. Okay? So maybe write that down at the bottom here if you've got some room. All stations to central to remind you of the ASTC as you go around the quadrants 1, 2, 3, 4. All right, finally, we get to the examples of what you need to do with all of this information. So example number 1, choose an obtuse angle. So we're only dealing with that second quadrant. Choose an obtuse angle to complete each statement. Cos of 60, cos in the second quadrant is going to be negative, right? Only sine is positive in that second quadrant. So cos is negative, hence why there's a negative sign in there. But what would the obtuse angle be to put it into that second quadrant? Yes, if this is 60, remember the 180 minus theta stuff that I wrote all over that diagram? 180 minus 60 is 120 degrees. Okay, so it would be negative 120 degrees because it's in that second quadrant. Okay, let's try it again. Sine of 24, if I push sine into the second quadrant, it's still positive because sine is positive in the second quadrant. What is the angle? 180 minus 24, which is 156. Okay? Next one, tan. Push it into the second quadrant is going to be negative. Only sine, am I saying that enough? Only sine is positive in the second quadrant. So the angle is going to be 180 minus the 38, which is 142. Tan of 62, tan in the second quadrant is negative, okay? And 180 minus 62 is 118. Yeah? See all that stuff we just went through? If I just showed that to you, go, why? But now you kind of hopefully have some idea as to why or where I'm getting this stuff from. Yes? For this one, it said that I wanted to choose. So choose means all of those ones I was pushing into the second quadrant. Okay? There will be times when I'll be looking at the other ones, but those ones were all in the second quadrant. Okay, next part, question 2. It says find the exact value of, and now as soon as you see those words, exact value, think of those triangles, those lovely triangles that, okay, when you do maths in year 11 and 12, Nessa has made somewhat of a formula sheet. It doesn't have everything on it, but it has a few key ideas. These triangles are actually on it. So You will have these if you do advanced maths, you will have these triangles, but it actually is faster if you just know them. Lily?
Does that mean that they will be in the HSC paper?
Yeah. Yeah. So it's actually attached to the HSC paper. So here are the triangles, again, written down for you. There they are. So if I want to find the exact value of sine 30, now 30 degrees is a lovely acute angle. We like acute angles. They're the ones we're familiar with. Acute angle, 30 degrees. I can just come over here. Here's my 30-degree triangle. Sine is opposite over hypotenuse. So opposite is 1 and hypotenuse is 2. So that is simply equal to a half. That was the easy one. Okay? All right. What happens though if my angles are no longer the acute angle? It means I'm putting my angles into the second, third or fourth quadrant. Okay? Because then I have to start worrying about positive and negatives in here. Okay? So what you can do, what I would like you to do, is always draw a little all stations to central diagram over here. You don't need the circle part, you just want the A, S, T, C. Alright? So if my angle is 120 degrees this time, which quadrant am I in? The 1, 2, 3 or 4? 2. So I have an angle in here. Is cos of something in that quadrant going to be positive or negative? Negative, because it's cos in the sine quadrant, right? Okay, negative. We know there's going to be a negative sign in here. So negative. It's going to be cos, and we want to find the reference angle, because our triangles over there are only acute angles. We want to find the reference angle that is equivalent to that. So we're kind of doing this in reverse. What's 180 minus 120? 60. So 60 is the reference angle. When you do these on your test, and there is a few of these on your test, well, I always say too much, don't I? You are asked to always write the question with the reference angle in it first, which means it wants you to show that line before you write down what the exact value is. So now, the exact value part, leave the minus sign in there. Cos of 60 means I come to my 60-degree triangle. Cos is adjacent over hypotenuse, which is a half again. All right, let's try it again, doing the same process over and over. Tan of 225. So let's draw our little all stations to central so we can see our quadrants. 225, which quadrant are we in? The T quadrant. We're somewhere down here. What we should do is probably write the little...
Do you go anti-clockwise?
Yes, you do. What is the reference angle for 225? Ooh. Okay. You are doing, this is the 180 plus theta quadrant. So you want to subtract 180 off that. 225 minus 180 is a 45-degree angle. It always goes to the horizontal. I'm going to draw it on the diagram there for you. To the horizontal. Now, I'm doing tan of 225 and I'm in the T quadrant. So it's going to stay positive. So it's going to be equal to a positive tan of 45. Okay, so I've changed it into the acute angle. I've checked the sign and I found the reference angle. Tan of 45 using my triangle. Tan is opposite over adjacent. 1 over 1 is simply 1. Trust me, the answers aren't always the nice ones. We haven't had any surds in here yet. Okay, one more. Sine of 330. What quadrant are we in? The last one, I think I heard Maya say, yep. So all stations to central. 330 would be in there. What is the reference angle? 30, excellent. Because you're doing 360, this is the 360, and you're subtracting off the 330 to find the 30-degree angle. We're doing sine, but we're in the cos quadrant. So it will become negative sine of 30. What is sine of 30 over here? Opposite over hypotenuse is a half again. Negative a half. Alright, so that is what you need to practice in exercise 7F. Remember, I think it's particularly from question 9 onwards is where you're going to have to rationalize some denominators as well in there.